right, hello folks. So we're going to pick up with MaxFlow. I understand that Monday's recorded lecture went well for those of you who attended. I mean, I'm sure some of you just watched it for yourselves. But we are going to pick up where the Monday presentation here left off. We had already introduced the maximum flow problem. And last lecture, the Monday lecture, was concerned a great deal with sort of structural issues. We talked about path decomposition, which says that really every flow is just a combination of, at most, m flow paths and flow cycles. Right, and the total value of the flow is just the total value of the flow that's traveling all the paths from the source to the sink. Then we talked about the sort of deciding when a graph has, when there's a non-zero flow in a graph, right? And that led us to the notion of cuts, right? Which are these things that are dual to flows. The argument that we showed last time was that there is a flow, a non-zero flow if there's no cut. And sorry, this is all qualified by ST. So no non-zero. There's a non-zero flow if there's no ST cut. No empty ST cut, and vice versa. There is an empty cut if and only if there is zero ST flow, zero ST max flow, that is. Right? And then we started talking about flow algorithms. Right? And this idea of deciding whether, first sort of verification, deciding whether an existing flow is maximum. And that led us to talk about residual graphs. Right? So the residual graph allowed us to generalize this argument about non-zero flows being dual to empty cuts, right? We showed that you have that your current flow is maximum if and only if you have a zero residual ST cut. And finally, we introduced, if your flow is not maximum, the notion of an augmenting path in the residual graph, which provides a way to improve on the flow that you currently have, which is not maximal, right? So this is a path of edges of non-zero, of positive capacity. In the residual graph. From S to T. And if you can find one, then you can increase the amount of flow on all of those edges on that path. And this increases the total value of the flow from S to T, bringing you closer to the maximum. At the same time, because you're increasing flow on a path, you continue to follow to satisfy the balance constraints and the capacity and the capacity constraints and so forth. So this gives you a new valid flow, but one which has a larger value. Okay, and so that's kind of where we left off last time, if I'm understanding correctly. With the idea that this basic idea of an augmenting path can give you an algorithm for computing max flows, right? And so the simplest and most generic augmenting path algorithm says while there exists an augmenting path, find one, and augment on it. Right? And if this algorithm terminates, it's going to terminate when there is no augmenting path, which means that it is going to terminate when you have a maximum flow. Right? There sort of is a trivial point about this, right? This doesn't say how much you should augment. Obviously, if you found an augmenting path, you might as well augment as much as possible. What's the limiting factor on how much you can augment on a particular augmenting path? Yes?
The capacity.
Exactly. So this is sort of implicit that you're going to augment by the minimum capacity on the path, which is often the particular edge which has that minimum capacity is called the bottleneck edge on the path. You'll sometimes talk about the bottleneck capacity, but that really just means the minimum capacity on the path. Okay? And so we showed last time, thanks to these sort of structural results, we know that when this algorithm terminates, you're going to have a maximum flow. Right? Now this does leave a question. Does this algorithm terminate? Right? And we started talking about that last time. Right? And so for starters, we said, suppose that you have integer capacities. Okay? This is very common. And remember that we're going to use capital U to represent the largest capacity anywhere in our network. So if we have integer capacities, can we say for sure that this algorithm terminates? Yes?
Because every time we're adding at least one flow, and we know what's the maximum flow possible.
Good. So there's two things here. The first thing to observe is that the maximum flow is finite. Right? How do we know that the maximum flow is finite? Oh, actually, we know it from a thing that I left off of our list of what we learned last time. Right? So how do we know that the maximum flow is finite? Yes? Exactly. So we had this max flow min cut result. Right? Says the maximum flow, well, is actually equal to the value of the minimum cut. Right? Now, if you have integer capacities on your edges, then every cut is going to have an integer capacity in total, right? And so that actually tells you that the maximum flow value is integral if the minimum cut, if the edges all have integral capacities, and certainly tells you that it's finite. Right? So the next piece of the argument that you made was that we're always finding at least one unit of flow. Okay? But this actually requires a little bit of induction work. Right? So, okay, the first time I look for an augmenting path, all the capacities are integral. Right? But what happens next? Well, I find that augmenting path, all the capacities are integral, and that means that the bottleneck edge is an integral edge. And so the amount that I will augment that path by is integral. So every capacity changes by an integer, which means that every capacity is still integer after the augmentation. Okay? So each integer augmentation increases the flow value by an integer, so at least one, and keeps all capacities integral. Which means that we can iterate this argument, right? That the next augmenting path that we find will also be an integral augmenting path, and that will make the third one an integral, and so forth. So we're always augmenting by an integer amount, which means we're always augmenting by at least one. And since the actual maximum flow is finite, we will reach that maximum flow within a finite number of steps. Yes? Okay, now this actually shows us something a little bit stronger than we get from max flow min cut. It tells us a corollary. If the capacities are integers, there exists an optimal flow, or a max flow, that is integral everywhere. Right? So max flow min cut tells us the value of the cut of the max flow is integral. Okay, but this says that actually you can construct that max flow using only integer flow values. Right? I can create a flow of integer value by, say, sending half a unit this way and half a unit that way. Right? The value of that flow is 1, but it's a fractional flow. Okay? This is saying this is actually always an integral max flow, which is useful. We'll rely on that at various times. But as I just argued, there may be other optimal flows that are not integral. But at least one of them is. Okay, so now we've said finite time, right? This does terminate, but what can we say about how long it takes to terminate? Well, at the moment, we're just saying that we add a unit, at least a unit of capacity on every augmentation. So the time to terminate is going to be determined just by the value of the max flow, right? Whereas at most, the value of the max flow in this integral case. So can we bound the value of the maximum flow? Yes?
U times n.
Good. So there's a couple of different ways to bound this, right? So in a so-called simple graph, which means that you're only allowed to have one edge between any pair of vertices. Okay. We know there are at most n edges leaving the vertex S, the source vertex, and each of them has capacity at most U. And so this is a particular cut in the network, right? A cut with has S on one side and everything else on the other side. And so we know that the maximum flow value is less than the value of that cut. And so this gives us a bound on the maximum flow. Okay. If you're allowed to have a so-called multigraph, right, where there might be parallel edges in the graph with the same endpoints, can we give a bound on the value of the flow in that case? Yes. How come?
Because there are
total edges in the graph each of capacity U.
Great. So we can just say that, well, this is the total capacity of the graph. Or we can say that whatever the min cut is, it has at most m edges, and each of them has capacity, right? So again, max flow min cut gives us the m times u bound, right? Okay, and what's the time to find a single augmenting path? Yeah? And how would you do it? Yeah, just sort of a breadth first search or anything like that, right? We find an augmenting path by BFS or whatever other search method we want. And so that gives us a runtime of order, well, m times m nu, or order m squared u, depending, right? And so this is polynomial in the number of vertices and the number of edges and the largest capacity, right? More generally, it's order m times the flow value. Now, is this a polynomial time algorithm? By the sort of normal definitions of polynomial time algorithms? Yeah?
No, because it's exponential in the length of U.
Right. The problem is that the standard definition of a polynomial time algorithm is one that has a running time which is polynomial on in the size of the input, where the input is typically represented in bits, right? So this algorithm is not polynomial in the size of the input. Because the numbers are represented in binary, right? And so, in k bits, you can represent a number of size 2 to the k and end up with an algorithm with a graph that causes this algorithm to run in 2 to the k time, even though the length of the input is only k. Okay? But this is what is known as a pseudo-polynomial algorithm. Which is referring to the fact that it's polynomial in the inputs in m and n, and the values of the numbers. So it's not as good as a polynomial time algorithm. Sometimes complexity theorists talk about this as being a polynomial time algorithm if you write all the numbers in unary, right? You just represent the number n by a series of n ones. Okay? But it's not polynomial. And so that sort of points us at the goal for this lecture, which is to achieve polynomial time algorithms. But before I get there, this was all about integers. What happens if you use rational numbers? Yes?
You can make them integers by multiplying by those.
Good. So if you're interested in solving the problem, what you can do is multiply out by all the denominators, right? And now you've got the integer problems. And now you've got an integer graph, and everything works, right? And so it's going to terminate, right? Now, again, this is certainly not polynomial, right? Now, the values of your numbers may look like u to the nth power, right? Because you're multiplying by n different denominators that might be u. Okay, so it's a very big number, but it's still finite. And actually, you don't have to actually multiply out the denominators in order to achieve this. If you just do your augmenting paths, right, you can notice that every augmentation is going to be some integer multiple of the lowest common denominator, right? And therefore, you are going to make a non-infinitesimal step towards the maximum flow in every step, right? The maximum flow is some number of multiples of the least common denominator. You're progressing by at least one least common denominator in every augmentation, okay? But now you're not even pseudo-polynomial, right? 'Cause, I mean, it doesn't really make sense to talk about pseudopolynomial with rational numbers because the values change just by scaling, even though the problem doesn't change. Okay. So with rationals, we're still finite. What if you use real numbers? There's the small problem of representing them in the computer, but let's not worry about that. Yeah?
I imagine the algorithm can do arbitrarily poorly by getting distracted by making small improvements that aren't actually getting it even close to the actual maximum.
Good. So yes, if you're if you're just trying to follow the rules for augmenting paths, we say find some augmenting path and saturate it. You know, augment by the bottleneck edge, right? If you do that in the worst possible way, right, you can arrange for an algorithm that might not terminate. Okay. Now, it's even worse than that. Like, if you have something involving real numbers and not terminating, what is a natural way to talk about the eventual value? Right, of some real number process that's going on forever. Yeah? Its limit, right? So you might hope, well, it might not terminate, but at least its limit value is the maximum flow. No, right? You can actually arrange for the limit to not be the max flow. Of course, this requires you to run your Maxwell algorithm in a very perverse way. You're always looking for the worst possible thing to do instead of the best, but it can happen. Okay? So all of this says we're still quite far away from polynomial time. And that's what we're going to want to get to in this lecture. Okay. So to motivate what we're going to do now, let's look at a particular example of how augmenting paths can go very badly. It's a pretty simple example. Just going to make this little diamond here. And I'll put some nice big numbers on the diamond. And then I'll just put this one edge here with capacity 1. Now, if I'm very foolish in my augmenting paths, how long might it take for me to find a max flow in this network? Yes? 2 times 10 to the 6. How come? It's not quite that bad, but it's close. So why 2 times 10 to the 6?
Well, I imagine if you just keep.
Oh, sorry, you're right. It is 2 times 10 to the 6.
Well, if you keep taking like the zigzag path to augment.
Exactly. You can imagine that for my first augmenting path, I would go like this, right? And there's a 1-unit bottleneck edge, so I can augment by 1 unit, right? What does the residual graph then look like? Yeah? Yeah, this edge gets flipped in the residual graph. It's now a 1-unit edge going in the opposite direction. Also, these are now, 1 less. Right? But the important thing is that I have a 1-unit edge in the opposite direction. So now when I do the next augmentation, I'll zigzag in the opposite direction. And I'll again get 1 unit. So each of my augmentations is a 1-unit augmentation. And I'll have to do 1 million of them or 2 million of them in order to get my entire max flow. Okay? So that is a bad approach to the maximum flow algorithm, right? What would be much smarter? Yeah?
Just go down the biggest capacities. So
Yeah. It seems to make sense to go after the biggest capacities because that way you're going to get a lot. It's sort of greedy, right? Greedy is a great strategy a lot of the time. America is founded on it. So if you just go after the maximum capacity augmentation, the most augmentation that you can manage at every step, right? We know that, that greedy does not instantly give you, right? There are some algorithms where being greedy just gives you the answer, right? Like minimum spanning tree, right? Being greedy does not give you the answer in maximum flow, but maybe it's a good way to give you a lot of progress towards the answer. So we are going to look at max capacity augmenting path being locally greedy. So if that's going to be our approach, maybe we should make sure that we can compute it. Can we find the maximum capacity augmenting path? Yeah?
Do that. You can binary search like a value, the value of edge you want to see if there is a path.
Great. So this goes back to the idea that capacity of a path is determined by its bottleneck edge, right? So some edge is the bottleneck edge for the maximum capacity augmenting path. So if we just try and identify which edge is the bottleneck edge, right? That suggests a binary search strategy, right? We speculate and say, okay, maybe this is the bottleneck edge. So if that's true, we don't need any edges smaller than this in the augmenting path, right? So let's just ignore all of the edges smaller than this one and see if there is an augmenting path consisting only of edges at least this big, right? And if there is, then we've lower bounded the bottleneck, right? If, on the other hand, ignoring all of the edges smaller than this one gives us no augmenting path, well, in that case, we've upper bounded the bottleneck, right? We know that we have to use a smaller edge in order to get an augmenting path. So we just, to find it, we can imagine doing a binary search on the bottleneck edge value. And so if we do that, how many of these binary search steps do we need? Yeah?
Log of n.
Exactly. Log m steps. And how long does a single step take? Yeah?
Just do BFS like M.
Again, it's BFS, right? We're just asking, is there a connection with edges this large, right? So order m per step. And we put those together, and we have an m log m time algorithm for a single augmenting path. Okay? So that's great. I mean, that'll work great in practice. If you really want to squeeze things down, you can do the smaller of m plus n log n, or m log star n. And with those things in there, it's kind of clear what sort of techniques you should use, right? So this is sort of another application of Fibonacci heaps, right? If you think about it, the bottleneck path problem is basically like the shortest path problem, right? You're asking for the shortest path from S to T, but you're measuring it differently. Instead of measuring it by adding the edges, you're just measuring it by the smallest edge on the path. And so actually, in that sense, it's kind of like a directed version of minimum spanning tree, right? Minimum spanning tree is asking to connect the whole graph with the cheapest possible edges. This is just asking to connect S and T with the cheapest possible edges, and it's directed, right? And there's a directed version of minimum spanning tree called minimum arborescence, which says here's S, and draw me a directed tree that reaches everything else, which you can solve using Fibonacci heaps in the natural way. And that directed arborescence also it includes the best bottleneck ST path in that arborescence. Okay. M log star n involves more of the tricks like we did to improve on Fibonacci heaps, sort of condensing parts of the graph and so on and so forth, which is much trickier in a directed graph, but you can still do it. Okay? So finding one augmenting path is pretty straightforward. The hard question is, how many of them do we need to find? Okay. Now you'll notice we're going to let's start again with integer capacities, and we'll come back later and revisit that. Okay, so can we say anything about how many augmenting paths we'll need to find if we have integer capacities? Well, this is an example of an augmenting path algorithm. So all of the bounds that we proved for augmenting paths still hold, right? It's going to be order MNU, for example. Okay? But that's not very interesting. We don't need a smarter augmenting path algorithm for that. So how can we improve on that bound, on the number of augmenting paths that we need? Okay. How do we use this insight that a large augmenting path ought to be making good progress? Well, we need to relate the size of the augmenting path we find to the value of the entire maximum flow, right? What we need to argue is that somehow we're finding a lot of the maximum flow in a single bound or in a single step. And so if we think about that some more, it basically comes down to arguing that there has to be, we're looking for the maximum capacity augmenting path. We need to argue that there are at least some large capacity augmenting paths, right? If we can say that there exists an augmenting path of large capacity, well, then the maximum capacity path is going to be better than that. So how would it follow that if the maximum flow is large, then there is a large augmenting path? Yes?
Because of like the max flow min cut, at least one cut has to be like 1/m of the flow or something like that.
So what do you mean by a cut being 1/m of the flow?
Yeah. Each like a flow corresponds to like you can think each unit of flow corresponds to like a 1 unit of like an edge. That's
So you're sort of talking about the flow kind of the flow kind of has to spread out over the various edges of the min cut, right? So this is certainly true, right? We know there are only m edges in the min cut, right? And so, you know, one of those edges has to be carrying at least 1/m of the flow, right? So that seems kind of useful, right? The problem is that that's not a whole path, right? That's only showing us one kind of moment in the path from S to T. We need an argument that there's a whole path of good capacity. Yeah? Good. Good. So path decomposition. So suppose that there is a residual flow. Suppose that the current residual flow is some value f. Okay. There is a path decomposition. Of that residual flow into, at most, m paths. Right? We showed that last time. Well, that implies that one of the paths has at least f/m flow on it, which means, and the only way that that path can be carrying f/m flow is if every edge has at least f/m capacity, right? So that implies that the bottleneck capacity is at least f/m. And so when we look for the maximum capacity path, we will find a path of at least f/m. Right? So we find at least a 1/m fraction of the flow value. Now that doesn't seem like a lot, but it's enough, right? Because that implies that the next round, the next residual flow, is at most f minus f/m, because we just used up f/m of the flow, which is 1 minus 1/m times f. So when we find a maximum capacity augmenting path, we are decreasing the residual flow by a factor that is independent of the flow. So in particular, m flow, if I do this m times, it's going to decrease the capacity by 1 minus 1 over m to the mth power, which is about 1 over e. Right? So m of these augmenting path calculations reduce f by a constant factor. Okay, that's nice, right? M augmenting paths reduce f by a constant factor, but we need to reduce it to 0 to get a max flow, right? I mean, it doesn't matter how many constant factors you reduce by, that by itself doesn't get you to 0, right? But here we can exploit something else. Okay, suppose that I tell you that the residual flow has gotten down to a half, right? Yes? They're integers, right? So if the, again, integer augmenting paths give us integer capacities by induction, and they're always integers, right? So if we have got the residual max flow down to a half in a graph with integer capacities, right? In a graph with integer capacities, the max flow is integral. And so the only way for the integral max flow to be less than a half is for it to be 0, right? So integrality tells us that we're done when the residual flow is less than or equal to a half, right? i.e., when 1 minus 1 over m to the t, sorry, let me be more precise. We can do t rounds such that 1 minus 1 over m to the t power times f is less than or equal to a half. That will be enough rounds to give us the max flow. Yes? And if we solve for that, right, we want 1 minus 1 over m to the t to be less than or equal to 1 over 2f. And that means that, roughly speaking, t should be about log, or about m times the log of f. Okay? Any questions about that? I haven't gotten any questions today. This must be all old hat to everybody. Okay. So is that polynomial? I mean, it still has f in it, right? Well, remember that each of our augmenting path calculations cost us m log m, and we need to do m log f of them. So it's m squared log m log f. Right? Yeah?
We know the f is bounded by mu.
Exactly. So this is order of m squared log m log of nu, or let me be more cautious and say mu, right? But that just pulls out another log m, and we're left with this log u term, right? So here we have log m plus log u. And that is polynomial, right? Because the number of bits that you need to represent u is accounted for in the size of the input. Yes?
Why isn't it just less than 1?
Less than 1 would be fine. I just wrote a less than or equal to a half here. Because if it comes out to, if it's exactly 1, you're not done yet, right? You might need to take one more augmenting path to get that last unit of flow. I could have made this a third or 3/4 or whatever, but I just wanted it to be something strictly less than 1. Okay. So we've got our polynomial time algorithm for max flow with not too much extra work, right? Now note, or sorry, I'll say that this is polynomial, but it's still kind of annoying because it does depend on the sizes of the numbers, right? Max flow is this sort of, it's a combinatorial problem. It's about the structure of the graph and so forth. And it's a little disturbing that the runtime of your algorithm should change if, say, you double all of the capacities, right? That's just a little bit weird. So formally, this is known as a weakly polynomial algorithm. It still depends in a polynomial way on the numbers. And something we're going to work towards is a strongly polynomial algorithm, which depends only on m and n. Okay? And this difference matters, right? Because a strongly polynomial algorithm would work correctly even if the input were real numbers, right? Whereas a weakly polynomial algorithm with real numbers could take an unbounded amount of time. Okay. And actually, let's think briefly about rationals. What happens if I give rational numbers to my maximum capacity augmenting path algorithm? Well, we can play the same trick of multiplying out all of the denominators, right? And what does that do? Yeah?
It'd be log of u to the n or something, and then the n, yeah. There's just
Exactly. So we can multiply denominators. Which makes our numbers increase to look like u to the m power, right? And so, but fortunately, log of u to the m is just m log u, and so it's still polynomial, but it's a worse polynomial by a factor of m. And again, you don't actually need to do the multiplication. You can check that your analysis works just fine even with, right? You redo the whole analysis here, but in terms of the lowest common denominator again. Okay? So it works. It's still polynomial. The runtime isn't great. Okay? Good. So that completes our algorithm, our first algorithm. That is polynomial time. I will show you another one, but let's take a short break first. Too much sitting. Get up, move around.
You always have the most interesting transportation that I've seen.
This one is from the river yesterday.
Maybe you should watch the second half of the lecture in a different part of the room for variety. Right? Just,
The bottom of the river.
You just took it?
Like straight. Yeah, and then washed it. Yo, is that lecture? It is. This is probably a better one though. What? This or this? But this one was cheaper.
That is superior.
in every way.
Did you also get this from the river?
What? Wait, where did you get that from?
From in the river underneath the Butte Bridge.
Oh my god, okay.
Nathan, where did you leave that?
Oh, it's up there. It's like all the time, but peace of mind.
How much did it cost?
Peter, do you think you can ride it?
Or maybe
Oh, wait, wait, wait. 1v1?
Oh,
Yo, we were doing
wait, this
right
one's
now.
slow.
Okay,
Wait,
wait,
this one's slow. I feel like you can go like 1v1. At least switch it.
you don't have
You're facing the wrong way. You gotta turn around. Yeah.
Oh no, I wish I was 50. If that was 50. Dude, oh my god.
you have the century. That one is very hard.
Oh my god. Okay, somehow did it.
I think it's easier if you go with the one and those are
It's close enough. Those are, we're safe here.
Yeah. Keep your elbows in. You don't. If they're out, you could. Having your elbows out can be bad for your rotator cuffs. You want your elbows in towards your side.
So true.
so maybe get that. I feel like log goes sideways. Where's Oliver? Yo.
I think I have to grade the problem.
No way, are you? Yeah, say it again? Say it one more time.
It does look
Rashad. Oh no. Oh, but it's pronounced Rashad. Okay. Okay, I see. I was trying to reconcile with whatever I got.
Yeah, you're grading this thing.
Yo, you're grading this week?
I'm grading problem.
No way. Are you grading this week?
All right, let's resume. So I've shown you this first polynomial time algorithm, weekly polynomial time algorithm. And it wasn't that hard to come up with, but it did require some creative thought, right, about how do you approach this problem and coming up with this idea of going after the maximum capacity path and then having this insight into how you can relate that to the maximum flow, right? And creativity is very hard. It's nicer if you can just kind of follow a mechanical recipe and get the answer, right? Differential equations, that kind of thing. So what I'm now going to show you is a mechanical way, a general technique for deriving these faster polynomial time algorithms by essentially taking any algorithm that works in the unit capacity case, where there are no, or in a case where the numbers are small, and figures out an elegant way to turn that into something that works for larger numbers, right? So, I mean, I don't know if I explicitly talked about unit capacities before, but obviously if you are, if all of your capacities are 1, right, then the running time of your generic augmenting path algorithm is order mn, right? It's polynomial and pretty quick if all of the capacities are 1. It only falls down when the capacities are large. So I'm going to show you a technique called scaling, which is a general technique to transform an algorithm for unit capacities to an integer capacity algorithm. Without having to do any thinking. And it's based on the obvious observation that any number is just a collection of zeros and ones. So in a sense, if we can handle the zeros and the ones, we can handle any number. We just need to break it down into pieces. And this was developed by Gabo for max flow problems. But actually, it was earlier developed by Dinitz for max flow problems. But Dinitz was publishing in Russian, and so Americans never heard about it until after Gabo figured it out. Okay, and the idea is to basically take your problem with its large integer values and just round them down so that they become small integer values, right? So you transform your large numbers into small numbers. And so now you can solve the problem fast. Now the rounding introduces a small error. So you correct the error by sort of unrounding the numbers. And then you have your answer. Okay. So in particular, I'm going to start. Let's suppose the maximum value is the max capacity is U. Okay. So what I'm going to do is I'm going to replace every capacity by a rounded down version of that capacity. Whoopsie. A rounded down version of that capacity. Right? So divide every capacity by U, and then round down to the nearest integer. So what possible values can I end up with at this point? Yeah? 0 and 1. Right? If there are some capacities of U, they'll turn into 1. Everything else will turn into 0. So now I have a 0, 1 graph, right? How long does it take me to find, how fast can I find a max flow in this 0, 1 graph? Well, I just said, right? We can solve this using any augmenting path algorithm in order mn time. Right? Now, we've got a partial answer, but now we're going to unround. And the trick, the key trick of scaling is to sort of unround, but only 1 bit at a time. Okay? So essentially what we're going to think about is we sort of divided everything down. We basically think of each number as just being a 1-bit number. Now let's take 1 more bit of each of the numbers. Okay? So we had numbers that were 0 and 1. Now we're going to take 1 more bit. So now our numbers could be 0, 1, or 2, or even 3. Okay? So need a new board. And let me start over now that we've sort of got the intuition of what's going on. So we're going to solve max flow 1 bit at a time. So initially, we're going to replace every number by 0 bits. Then we are going to solve max flow. But since we have 0 bits, the answer is 0. Now we are going to repeatedly shift in 1 more bit of our numbers. Okay. What does this mean? It means we double all the numbers, all the capacities, and then we add 1 to some of those capacities, the ones where the bit that comes in is a 1. Okay. Now, we had a solution to our max flow with the old capacities. We've just changed the capacities by doubling them and adding 1 in some cases. How can we get a pretty good solution to the new capacities? Maybe not optimal, but still pretty good. Yeah?
Well, you can just double, like when you double the, like everything, you can just double the flow that you're sending.
Exactly. So to resolve the max flow, we're just going to double all the flow values. And that's a great starting point. But we might not have a max flow at this point because we have increased some capacities, right, by adding 1 after the doubling. So we still need to find a max flow. How are we going to find the max flow? Well, we're going to run augmenting paths again. And so now the key question. How long does it take me to run augmenting paths after I have doubled everything? The time is order, well, I need to do m augmenting paths. And this is the new residual capacity, or residual flow value, after the shift and the doubling of the flow. So what can I say about the residual capacity of the new graph that I get when I shift in another bit? If I could argue that it's small, then I would conclude that my augmenting path algorithm would run fast. Yes?
The new max flow is less than equal to double the old one?
Well, it is true that the new max flow is equal to is at most double the old one, but in fact, we've already taken care of that by doubling all the flow values, right? So we had a max flow. Now we shift in another bit of capacity. And when we double the flow values, right, that sort of uses up all of the capacity from the doubling of the, sorry. Think of this in two steps, right? First we double all the capacities. Then we double all the flow values. OK, we're still at a max flow. But now some of the bits that were shifted in were ones. And so we have this graph which was a max flow, but now we're adding 1 to certain capacities. What might that do to the flow value? Yeah? Why would the new flow, would the residual flow after this be at most m?
For each edge, the residual flow increased by -1.
OK, so that's almost there. It's true that the residual flow increased by at most 1, but we have to be a little worried because a max flow does not mean that every edge is saturated, right? There might be some edges in the graph which have lots of residual capacity, right? What if the increases of capacity in some other edges created all of a sudden a path through edges of very large capacity that allowed us to have a very large augmentation? Yes?
The bottleneck of those would still be 1, because if not, you would have visited it before.
The bottleneck of the... OK, so you're saying that somewhere on that path there is an edge of capacity 1.
Yeah.
How can we prove that?
Well, if there wasn't, then it means that it has capacity 2, so it had capacity 1 in the last step.
Good. So you're arguing that if every edge on this path has capacity larger than 1, then they all had non-zero capacity in the previous step, and that means that you would have found an augmenting path in the previous round, and it wouldn't be there, right? So that's a path-based argument, which is absolutely valid. Let me make a slight tweak to it and talk about cuts instead. OK? So, and again, cuts and flows are dual, so it's really the same argument. The argument is that before the shift, we had a max flow, right? What does that mean? It means there was an empty residual cut. Now, what happens when we double all of the capacities? What can we say about that empty residual cut? Well, it's still going to be empty because we're also doubling all of the flows, right? So the double step, that residual cut is still empty. We've doubled all the capacities on it, but we've also doubled all the flows on it, so the residual capacity of every edge is still 0. In the add step, we only add 1 unit of capacity per edge. which implies we're adding only m units to the whole cut. In other words, the double and add step creates a cut of value at most m. And if there is a cut of value at most m, that implies that the new residual flow is at most m. Now, if the new residual flow is at most m, how long does it take us to find that new residual flow using augmenting paths? Yeah? M squared, right? A single augmenting path takes us m. We have to find m augmenting paths. So it takes us order m squared time to augment all of that residual capacity away and get back to a max flow. Okay. So that's the time for one round of scaling. How many rounds of scaling do we do? How many bits do we have to shift? Yeah? Log U. Log U rounds shift all the bits, which means that our overall running time is m squared log U. Okay. And we got this for free. Like, we didn't have to come up with a new algorithm. We just had to take any old augmenting paths algorithm and apply this general scaling technique of solving one bit at a time. And we'll see scaling several times. We'll see scaling several more times. It's a very general technique in combinatorial optimization. You'll notice that it actually gives us something a little bit better than max capacity augmenting path, because we don't have to worry about capacities. We're just using generic augmenting paths, all right? And that saves us a bunch of log m factors, besides being a simpler algorithm. Okay. On the other hand, it is still a weakly polynomial algorithm. But it's certainly the easiest of the weakly polynomial algorithms to implement. So that begs the question of how do we get strongly polynomial? We'll start that today. We'll finish on Friday. Oh, I won't talk about, you handle rationals as we discussed for the max capacity augmenting path algorithm. But from now on, we're really going to focus on integer values. And I'll leave the generalizations to you. Oh, this one's done. Okay. So strongly polynomial maximum. So if we want to be strongly polynomial, we're going to have to come up with a new idea, right? Everything about the algorithms that we've seen seems really tightly bound in with the values of the numbers. And if you have something that depends on the values of the numbers, you're by definition not strongly polynomial. So we need some other way of understanding progress, right? Here, our progress was measured against the value of the maximum flow, right? Here, it was measured against the number of bits that we had shifted in or that we still needed to shift in, right? And both of these depend on the numbers. So to get a strongly polynomial algorithm, we need to try something different. And we're going to go back to sort of looking at max flow min cut from a different perspective. So our worry is, right, we've got this network, and it's got a bunch of really big numbers in it, so it looks like there's a lot of flow left to be found. Okay. So to differentiate two graphs, or two situations, here are two graphs with m edges. Okay. Now, both of these graphs have the same number of edges, but one of them has a much larger flow. Why? Or to put it a different way, is there a way that we can look at this graph and say, you know, there's just not that much flow possible in this graph compared to this graph over here? Yeah? I mean, these both are connected, right? They both, I mean, in both cases, you have a path from that visits all of the vertices.
The degree of connectivity is there.
Ah, so you're saying this has a very large connectivity from S to T. Well, that sort of is that's circular. That's the definition of max flow, if you think about it, right? Is how well connected are S and T. But looking at this graph, which has just as many edges, why is it not as well connected? Or how can you sort of convince somebody that it's not so well connected? Yes?
The number of different paths to reach T.
Well, that again is the definition of max flow, right? Yeah?
Degree is smaller for each node.
Degrees are smaller. OK, I can fix that. Now they both have small degree. Well, except S and T. Yeah?
S and T are farther apart.
S and T are far apart. OK, now if S and T are far apart, what does that tell you? It tells you that every unit of flow that's traversing from S to T is going to have to use up a lot of the capacity of the graph. And so it's more expensive in capacity in this network than in this network to send a unit of flow. Okay? And that's what the strongly polynomial algorithms are based on, is by looking at distance in the residual graph. As a sign of progress. So until now, we've been talking about finding a max flow by just comparing the flow we found to the flow that remains to be found. Now, we're using what's called a dual technique. We're not looking directly at the objective function. We're actually looking at something that fights against the objective function. Okay. We're going to measure progress by saying that S and T are getting farther and farther apart from each other. Okay? And in fact, what can we say? I can represent this by a distance function. I can subset it by f, the flow that I found, to say that I'm looking at distance in the residual graph, right? Once this distance is greater than n, what can I say? Yes? Right. Once the distance is larger than n, there are no augmenting paths. Why? Yeah? Fill that a little. There must be a cycle in what?
In any path between S and T and the augmented path.
You mean if the path is longer than n? Yeah. Right. Yeah, so exactly. If there's an augmenting path, right, then unless there's a cycle in the path, you can only visit each vertex once. You can always take cycles out of a path, right? So there's an augmenting simple path, right? So if there's an augmenting path, that implies that there's an augmenting simple path, which means that its length is at most n minus 1, because there's only that many vertices to occupy the path. Okay, so the contrapositive is that if the distance is larger than n, if there's no path of length n minus 1, then there's no path at all. And that means there's no augmenting path. So that's our new goal. Instead of trying to increase the flow from S to T, we're going to try to increase the distance between S and T. Make sense as a goal? So, any thoughts on how we can increase the distance from S to T? Again, we're not leaving the augmenting path world. We're still going to work by computing augmenting paths. But if you want to increase the distance from S to T, what would be a natural augmenting path to look for to cause that distance to increase? Yes?
Shortest path?
Yeah. So if your goal is to make S and T far apart, then you need to destroy any short paths between them. And so that's the next algorithm we're going to look at, is shortest augmenting path. Okay. So remember, when you find an augmenting path and you saturate it, right, by pushing flow that is equal to the bottleneck edge, right, you remove that path from the residual graph, right, because you've destroyed one of the edges on the path. So that seems like a really good thing to do, right? If you want to make S and T far apart, you need to destroy short paths. Augmenting along a path destroys the short path. What could go wrong? Well, maybe you create a different short path, right? And that's where the work of analyzing this algorithm is to sort of show what happens when you, to show that you don't create short paths as you're destroying short paths. But before we get there, how quickly can we find a shortest augmenting path? Yeah? BFS, right? You just take all the residual edges, and a BFS will give you the shortest one. Notice that there's no lengths on these, right? We're just counting the number of edges on the path, right? So BFS is the right way to get the shortest one. And so oddly enough, this is actually easier than finding the max capacity augmenting path, right? So it's very fast to find them. So the question is how many? Okay. And we're going to show that that is bounded by a polynomial. Okay. And I don't think I'll be able to show you the whole thing today, but I can give you the first piece. We want to show that eventually S and T get pushed apart. I'm going to show you that at least they don't get closer together. Okay? I'm going to show that shortest augmenting path does not decrease the distance between S and T. Okay. In fact, I'm going to fill in a little. I'm going to say a little bit more. For any vertex V, I'm going to let d of V denote the distance or let me just write it as d sub f of S and V before the augmentation. And d prime of V is the distance afterwards. Then the new distance of V is at least the old distance of V. Okay. So I'm going to show you that the distance from every vertex to S is increasing. By symmetry, you'll also find that the distance from T to every vertex is not decreasing. Okay? So everything is getting farther apart, just like in our universe. To prove this, I'm going to assume for contradiction that prime of v is less than d of v, and derive a contradiction. So let's start drawing pictures. Okay. So how did this happen when we did our augmenting path? Okay. We started with S, and well, suppose that the augmenting path, let's focus on a particular v. Let's take the v of minimum possible distance that violates our rule. So we find the vertex that's closest, minimal d prime of v. Find the vertex that got closer and the closest among all of the vertices that got closer. Okay. How did that happen? So here's S, and there's some path, and eventually, this is after, right? And the path eventually reached V, and V got closer to S. So what can we infer from the fact that V got closer? I claim that one thing we can infer right away is that the augmenting path had to go through V. Okay. Actually, no, sorry. Let me tell the story a different way. So here's V, as we said. There's some vertex W that comes before vertex V, right? So this is the new shortest path to V, and W comes just before it. Now, what can we say about W? Well, W is closer to S than V is. So what does that tell us about W? Yeah? Exactly. So W is closer than V. So W did not get closer to S, right? Now we also know by definition that d prime of V is just equal to d prime of W plus 1. Yes? So how did this augmentation occur that caused d prime of V to decrease, even though the distance of W was not decreasing? Okay. So suppose that this edge from W to V suppose that it has, I claim that it had 0 residual capacity before the augmentation. Okay. How can I justify that claim? Suppose that this edge from V to W had non-zero capacity before the augmentation. What would that mean? So after the augmentation, this had length d prime of W, right? Before the augmentation, there was a path from S to W of length d of W, right? If this edge also existed in the residual graph before the augmentation, what would that give me? Well, I could follow the path from S to W and then follow this edge, right? That's a path to V, right? If it was non-zero, then we had a path from S to W to V of length d of W plus 1 to V before the augmentation. Right? Okay, but that length, right, d of W plus 1, right, that would imply that d of V is at most d of W plus 1, because there is that path. But that's less than or equal to d prime of W plus 1, because W didn't get any closer. Right? But d prime of W plus 1 is what gave us what gives us the new length of the new distance of vertex V. Okay. So that would tell us that V actually didn't get closer, right? That the new distance of V is at least the old distance of V. So that's a contradiction. Okay. So d of WV, or sorry, edge WV, had 0 residual capacity before the augmentation. Now it has residual capacity because it's being used to make the new path for V. How did that happen? How did WV end up with residual capacity after the augmentation? Yes? Exactly. This implies that the augmentation added flow to edge VW. Why did it do that? What's our augmentation rule? Well, we did a shortest augmenting path, which means that VW was on the shortest augmenting path. Right? But that means that the distance of W before the augmentation was equal to the distance of V plus 1. And that means that the new distance, that the old distance of V, which was d of W minus 1, is upper bounded by the new distance of W minus 1, because W didn't get closer, right? But d prime of W is d prime of V minus 1. And so the distance of V is less than the prime distance of V, which means that V didn't get closer. And so that gives us a contradiction to our assumption that V got closer. Okay. So these two boards show us that at least nothing is getting closer as we do shortest augmenting paths. We're not creating shorter paths. Starting next time, I'll prove to you that in fact things get explicitly farther. They don't stay the same distance, but they actually get farther away from each other. Okay? I'll be posting a homework later tonight, and I will see you on Friday.